Hello students, in this video we are going to check about multi-objective optimization. So there can be a question that can there be more than one best solution? So this introduces us to a concept called multi-objective optimization. So let's take a challenge where we have phone A, B and C. Phone A is excellent battery, average camera and high price. And phone B has good battery, excellent camera and medium price. And phone C is average battery, good camera and low price. Now, which one will you prefer? Right? So now we may have, there is no single perfect answer to select all these phones. Right? So suppose if I just choose the battery, obviously I have to compromise on the price. So there is no single perfect answer. So this is an example of a multi-objective optimization. Many times the optimization may be multi-objective in the terms of I should have an excellent battery, at the same time the price should also be optimal. So there can be different objectives for my aim. So what is multi-objective optimization? Simultaneously optimizing two or more conflicting objectives. So common engineering problems can be maximum speed versus minimum fuel consumption. Of course, they are so conflicting. Maximum profit versus minimum cost. Maximum accuracy versus minimum execution time. So why is it difficult? Okay, so there is something called the trade-off concept. Can a car be fastest, cheapest, safest, and at the same time lightest? So, for example, if you want the car to be fast and safe, obviously you have to compromise on the power part of it. Okay, so the safety cell will be heavy, so it can never be lightweight, right? If you want it to be safe, you cannot have a lightweight cars. Suppose if you think about cheap and the lightest, it requires the basic material, small engine and minimal parts. So it is conflicting. So no, there cannot be a car which is fastest, cheapest, which satisfy all these conditions. So there is always a trade-off between objectives, right? So every day, if you take an everyday's example, some examples of multi-objective trade-offs are high salary versus low stress, large house versus low cost, high marks versus less study time, and so on. So there are two types of optimization. One is a single optimization, and the other one is a multi-objective optimization. So single objective optimization focus on only one goal, so results in one best solution, and generally it is easier to solve, right? But multi-objective optimization, it focus on multiple goals simultaneously. Okay, it may result in many acceptable solution. So, and again, it is more complex to solve and evolve. So let's take a engineering example, designing a drone, as we discussed in the previous lecture. So my design objective is maximize the flight time, minimum weight, maximum speed, and minimum cost. So the engineer can never uh, balance all these objectives. Okay, so can never design a drone with these conflicting goals. So there is a concept called Pareto dominance. Okay, suppose I just say student A has a marks of 90 in academics and sports 80. Student B has a marks of 85 and sports 70. So now student A dominates student B in all aspects. So we say that student A is the dominates candidate and student B is the dominated candidate. So what is Pareto dominance is a solution dominates another if it is no worse in all objectives and it is better in at least one objective. So it should be better in one objective and it should be not be worst in all the objectives. So that is the major one. Example, if you take a laptop X, Y, Z, if you compare X and Z, the price is the same. But if you take the performance, laptop Z dominates X, right? So the dominating option is laptop Z and the dominated one is X and Y is a trade-off choice, right? So it has a better performance. Of course, we have to compromise on the price. So that is a trade-off choice. So I hope now you understand what is the Pareto dominance, what is the trade-off. And the next one you have is the Pareto optimality. It says that there is no single best solution for any optimization problem. So you see this case, car A, B, C. The cost is cheap for car A, but the speed is slow. In B, expensive and fast. In C, it is medium and medium. So all these cars, none of the car dominates the other. If you see their performance, all these three belongs to the Pareto optimality set. Right? There is no single best solution. None of them can dominate the other. That is what is the Pareto optimality. So if you talk about the Pareto front, it is a visualizing the trade-off. It is visualizing the trade-off. When you plot performance versus the cost, the resulting curve is the Pareto front. So every point on this front is a valid compromise. And there isn't one universally best solution, only a set of best trade-offs available. Right? So practical utility, where are we using this? So where is this Pareto front useful? So a company CEO prioritize low cost. In terms of customer, if you talk, he may not concentrate on the cost, he may concentrate on the quality. An engineer may concentrate on the easy manufacturing. So the Pareto front lets the decision maker choose the best solution according to their specific priorities and constraints. So there is one more concept called epsilon dominance. So if you see these two cases, phone 1 and 2, the battery lasts for 10 hours. Here the battery lasts for 10.1 hours. So will you care about this difference? No, 10.1 doesn't make a difference. So such a small differences is called as the epsilon dominance. So phone 2 dominates phone 1, okay, in a small epsilon difference. So epsilon dominance treats a very small difference as equivalent, reducing unnecessary comparison. So we don't compare these two because there is no difference at all. What are the key benefits of epsilon dominance? So you can search, a faster search is there because you eliminate such cases. Computation, the better diversity among the final solution because the small differences are ignored and there will be diversity among the final solution. Simpler decision making for the engineers. So, and the third concept is called the robust optimization. See, whenever you try to optimize, suppose you design an umbrella, you cannot say that I'll use this umbrella only for sunny days. I won't be using that for rainy days or windy. If there is windy, this umbrella won't work. So you cannot tell in that way. Obviously, your design should be robust, which withstands sun, which withstand the rain as well as the wind. So this is called robust optimization, where it finds the solution that continue to perform even when the condition changes or uncertainty arises. So this is some real world example. This is a Google map. So Google map, it works, it provides you the good route even when the traffic changes, right? And power grid, it remains stable even when the power demand fluctuates. And you say the network routing, it stay connected despite individual link failure, immediately it adapts and it just do the robust optimization is handled. It stores the fat to survive across different uncertain climates. That's about the camel. So if you take about what all the concept that we studied here in this video is, we studied about single objective optimization, multi-objective optimization, then we studied about the Pareto dominance, Pareto front, epsilon dominance, and robust optimization. So if you take about live real world engineering applications, some examples where this multi-objective and robust optimization is used are autonomous vehicles, smart grids, cloud computing, wireless networks, robotics, healthcare, manufacturing, supply chain. So now this is about optimization. In the next chapter or the next hour, we'll be discussing about how this optimization can be evaluated. That is the performance indicators. Then we will also discuss about statistical analysis and the introduction of no free lunch theorem.